Hi everyone. In this video, we are going to continue the proof of the finite R transform theorem. We are going to, because the proof is quite long, even given the pitching lemma, we are going to split it into two. In the first part, we are going to prove a little lemma and a special case of the finite R transform theorem, which we'll just call Lemma A. Actually, at this point, it's not obvious why it is a special case, but we will see it afterwards. And anyhow, we'll prove this lemma. And then in the next video, we are going to prove lemmas that goes by the name B and C, because I like originality, and state a lemma called lemma D, which we'll prove later on, and continue from there. But anyhow, in this video, we are just going to start. And the proof of lemma A is actually, I mean, that's the kind of the non-trivial part of the proof. And some of the ideas in the proof are going to also appear in the proof of the R transform theorem that also uses the lemma itself. Okay, so let's just start. Okay, so as I said, we're going to prove a little lemma in lemma 1. This is part of the preliminary results we will need for the proof of the R transform theorem for the finite case, finite R transform theorem. And let's start with the little lemma, which is really a little lemma, just a nice little observation that we'll use, which is as follows. So say we have two real-rooted polynomials, G and H. Recall RRP is an abbreviation for real-rooted polynomials. And assume they both have positive leading coefficients. They can have any degree, but a positive leading coefficient. And let's assume that their sum, which we also denote by F, is also a real-rooted polynomial. And maybe this is a good point to stress, and we'll see and talk about that in the last part of the course when we talk about interlacing, but that's just a baby case, that the fact that G and H are real-rooted polynomial doesn't imply by itself that their sum is also a real-rooted polynomial. And you can take many examples, but like a typical example really, but maybe a simple one would be to take g of x, which is this function, like a nice parabola with one at the minimum, and then just add to it a line. These are real-rooted polynomials. The simplest I could think of that will work. And you know, the parabola, when it stands on the line, it has no, it doesn't, never touches the right at 1, which is the minimum of this thing. This thing is also 1, so it doesn't touch the x-axis at all. So it doesn't have any real roots. The sum of G and H doesn't have a real root. Okay, so real rootedness is a property that you can't assume like is closed under like standard operations. It is closed for operations that we'll do, but in this example, this lemma, we actually need to assume that if G and H are related polynomials and if their sum is also, then something happens. Okay, then what happens? Then the claim is that the max root of the sum is bounded by the maximum of the max roots of the individual polynomials. And moreover, equality holds when all three are equal, like exactly when all three are equal. Okay, so let's see. Again, it's really an exercise, but let's just do it so that you'll get a sense of how you do those things. So let's denote by x0 the maximum root of f of their sum, which there is a maximum root because we assume it's real rootedness, the real rootedness of f, and assume by contradiction that this doesn't hold, that star doesn't hold. So let's look at this picture. So this is x0, it's the maximum root of f, and we assume that star doesn't hold, which means that both of these are to the left of x0. Right? The maximum is smaller, so both of them are smaller. So maybe this is the max root of G and this is the max root of H. And we know that G and H have positive leading coefficients. So this means that the behavior is such that from the max root onwards, they go up, right? Never visiting again the x-axis. So that's these pictures here. So this is G and this is H, and they go up from that point. And because x0 is to the right of these 2 points, when G and H, when you ask what's the valuation of those at x0, it's strictly positive, right? Each of them. But then this is a contradiction because f of x0, which is 0, right? X0 is a root, it's the max root, but it's a root of F. Well, F is the sum of G and H. So in particular, the evaluations sum up to F of X0, and each of them is strictly larger than 0 in contradiction to the left-hand side being 0. And, I will leave the equality if and only if part to you because, frankly, the entire little lemma could have been left as a little exercise. Okay, so that's that. And we'll use this thing. And now I want to state the lemma that we are trying to prove now. But just before that, let me do a little bit of a massage to the R transform theorem that we are trying to prove. So recall that the R transform for polynomial at the point W is the K transform, corresponding K transform shifted by 1 over W. And the K transform is, if you recall, was defined for the finite case as the maximum solution to this equation. And we defined the U operator to be such that it exactly captures that. So the maximum root of the U operator applied to P is exactly this thing. So really the R transform, looking on the left and right sides, the R transform of P evaluated at W is precisely this max root, right? Minus 1 over W. And so the theorem that we wish to prove, which we stated in terms of R transforms, you can state it in terms of the max root of this operator applied to different polynomials, right? So you can replace each of these, but let me erase that because it's a mess, with the corresponding maximum root of the U operator applied to the corresponding polynomial. And so you'll get this thing. So the theorem of the R transform is equivalent to saying that for every W larger than 0, the maximum root of the operator, U operator applied to the additive convolution. And then you have plus 1 over W because you have minus 1 over W, but you have twice minus 1 over W on the right-hand side. So I just shifted things so that you get 1 plus W to the left side. So this thing is at most the sum of the max roots of the individual, of the U operator applied to the individual polynomials. So that's what we see here. Right, so it's nice to state things in terms of the R transform, but for the proof, we are actually going to want to get to work with polynomials, and that's why we actually introduced the U operator. And if you look at it for a second, the statement says that for every W, something happens where the something has this parameter, which we call alpha, and alpha is chosen to be 1 over W. It's not chosen, it's set to be 1 over WD, but it's for every W, D is fixed, it's the degrees. So it's for every W. So instead of saying that, let's kind of decouple it and just prove that for every alpha larger than 0, the maximum root of U alpha and so forth satisfies this thing. So really we are substituting W for 1 minus 1 over alpha D. That's why you get the alpha D here instead of that. But now kind of there's no, it's just, the parameter alpha is kind of a new parameter. It doesn't involve W and D, and the W is now switched to be in terms of alpha. Nothing fancy, just kind of simplifying it as much as we can before proceeding to the proof. Okay, so the goal is to prove actually this kind of bottom line here. That for every alpha larger than 0, the maximum root of U alpha of the convolution of polynomials plus this alpha D is bounded by the max roots of the two operators, of the operator applied to the two polynomials. Okay, so with this, we are ready to state and prove a lemma A. So the lemma tells us that for every alpha, also 0 and D larger or equal than 2, that's the degree. And if you give me just one polynomial, the lemma talks about a single polynomial, not two polynomials. The other polynomial is in a sense x to the D minus 1, but let's not talk about it at this point. Then the maximum root of the operator U applied to the derivative of P is a most of the operator applied to P and minus alpha. You get this extra minus alpha in the bound. Okay, so if you compare it to what we're trying to prove, it seems that kind of Q is missing. and this doesn't appear. And that's really just because that's going to be kind of the something like x to the d or x to the d minus 1. And also, this is not going to be, it's going to be d minus 1 and so forth. But, the max root of this is going to be 0 because it's just x to the d essentially. So you don't see it there. And we are not quite ready to say what we mean by d minus 1 here and so forth for degrees that are not d minus 1. What I'm trying to say is that this lemma, even though it's not seems like that, it's a special case of this theorem, which we're trying to prove, and it will be used in the proof. But forget about that. We just want to prove this statement, okay? Regardless of whether or not it is a special case. So let's start. Okay. I should say that equality holds if and only if, and that's important for the induction, if and only if the polynomial has a single root, okay? Which in measure terms, I think of it as a constant measure. Okay, so actually let's start with that if and only if part, just proving one direction of that. So let's say that you are taking the polynomial p to be this form. Let's just calculate. So the derivative of p is just this thing, right? dx minus lambda to d minus 1. And so now you can actually compute u alpha of p, which is just p minus alpha dp. So you can pull out x minus lambda to the d minus 1 from both terms, and you will be left with this thing. And so the root, I want to take the max root of this polynomial, and it has two roots, lambda with multiplicity d minus 1, and lambda plus alpha d, because of this thing, with multiplicity 1. And the max root is really the latter one, right? Because alpha and d are larger or equal than 0. So lambda plus alpha d is larger or equal than lambda. So the max root of u alpha p is lambda plus alpha d. So that's this thing. Now we need to compute the max root of u alpha applied to the derivative. Right here we computed the derivative in order to compute that. Now we have to compute the second derivative. So okay, so the u operator applied to the derivative is the derivative of p minus alpha times the second derivative of p. That's the derivative of p that we computed, and that's the second derivative. And again, you can pull out now d minus 2 factors of x minus lambda. You can also pull out the d, and you will be left with this thing. And again, this is, so the max root is either lambda or lambda plus alpha d minus 1. And it is lambda plus alpha d minus 1 because because alpha is larger or equal than 0, and d is at least 2, even at least 1 would be enough. So anyhow, the max root of u applied to the derivative, which we see on the left-hand side, is lambda plus alpha d minus 1. Everything is exact. So indeed, we get the equality, right? Because this thing is lambda plus alpha d, and this is lambda plus alpha d minus 1. So we gain this minus alpha. You can actually see it here if you want. So I chose here one polynomial, p of x, which is xx minus 1, x plus 3. And then the green line is u applied to p, and then the purple is u applied to the derivative. And you can and you should consider the difference between, now it's like between 6 to the left and 6 and to the right of 8, the difference between the max roots of the purple and the green lines. And as you change alpha, which is a here, you can see that this difference is always at least alpha, and it seems to approach it, by the way. But anyhow, if you set it very close to 0, you get there, getting closer and closer, but it's always at least alpha. So what did we prove so far? We proved the one part of the if and only if direction. We proved that if the polynomial is of this form, then equality holds. Okay, and that will be used in the entire proof. So now let's go back to the actual proof, like the main part of the lemma, and we're going to prove by induction on D, when you can take D at least 2, because if D is 1, well, actually the lemma doesn't say anything, but anyhow, the moreover part is enough. So we proceed by induction on D, which is at least 2, to prove the lemma. The base case is going to be also quite explicit now. So we are going to take d equals 2, polynomial of degree 2, and it always has this form, right? because we assume it's, I mean, it doesn't have to be monic, but for simplicity, let's assume it monic. What's important is that it's a positive, it has a positive leading coefficient. And we can assume that lambda 1 is larger than lambda 2, because the case lambda 1 equals lambda 2 we just handled, right? And this is what we want to prove, just as a recap. So first of all, let's look at, if we just move this alpha here, let's look at this new left-hand side, which is this thing. So and let's call this thing R, and let's compute it. So what's R, which is the alpha plus maximum root of U alpha dp? Okay, so P is this polynomial. Again, the base case is going to be just a calculation. So dp is going to be, you can differentiate a degree 2 polynomial. It's this expression. And U alpha of that, then you should differentiate again and substitute and multiply by alpha. But the differentiation of that is just 2. So you get what we had before, minus 2 alpha. Good. And now just playing with a little bit, you see that, sorry, before that. So this is the polynomial. And so the max root of that polynomial, this is the polynomial. So this is a very simple polynomial now, and the max root is just the root of that polynomial. It's a linear polynomial. It's this thing. I just, do the equality to 0 and move everything divide by 2. And just playing with a little bit, you get this thing. So R is 2 alpha plus the average between lambda 1 and lambda 2. So that's the left-hand side if you move the alpha there. As for the right-hand side, it's actually kind of more annoying because when you differentiate, you get lower degree polynomials, so it's easier to compute the max root. Now we'll have to slightly work harder. So U alpha P is just this thing, right? Because this is P and this is its derivative, and we multiply by alpha and subtract. And just kind of playing with it a little bit, taking the minus 2 alpha to as the coefficient of x, you get that this is a U alpha P of x. Okay. Now, let's evaluate U alpha P at R. It's not clear why I want to do it, because that's not what I want to do. I want to prove this things about max roots. I don't really care about R, which is the value of the left-hand side, the new left-hand side, but let's just do it for a second. So what is U alpha P evaluated at R? Well, I just really copied U alpha P, and instead of x here and here, I substitute R. And this is R as a reminder. Now, the point is that let's try to evaluate everything, to express everything in terms of R for now. So the point is that, this thing, the coefficient of what was x and now is R, is exactly twice R minus alpha, right? Because this is R. So we can substitute that and rearrange a little bit, right? You get so you get 2 alpha R because of this alpha here, and you have a minus 2R squared, and you had an R squared here, so you get minus R squared, so kind of these go like that. And the rest I left unchanged. Now let's do that again, but for this expression. So what is lambda 1 plus lambda 2? Again, from the definition of R in terms of alpha, it's twice R minus 2 alpha, or 2R minus 4 alpha. So again, rearranging, you get this expression. I never touched that so far. And now, if you stare at it for a second, you'll see that this is a minus of this perfect square, R minus 2 alpha squared, right? Just this part. But R minus 2 alpha, again, looking at R, is lambda 1 plus lambda 2 over 2. So this whole thing is that thing minus the average of lambdas squared. And then you had this thing that we never touched, the plus lambda 1, lambda 2. But we know how to kind of incorporate that. And so we get the minus of lambda 1 minus lambda 2 over 2 squared. Like it's a plus b squared, a minus b squared, stuff like that. The thing about this is that because lambda 1 is different than lambda 2, because we assume that's the case, because otherwise it was the moreover part, then this is not only non-negative and non-positive, it's actually negative. Right? You have a minus of something which is non-zero squared. Good. So we just proved that U alpha P evaluated at R is negative. So what does it say about the max root? Because we don't care about that particularly. So the picture is this, right? P was a degree 2 polynomial, and therefore also U alpha P, right? It's this polynomial. It's a degree 2 polynomial. It has a positive leading coefficient. It's monic, because we assume it's monic for simplicity. It's all the same. And we just showed that at R it's negative. So if this is the U alpha P or parabola, it's happy, and at R it's negative, it means that the max root has to be to the right of R. Max root of this polynomial, right? Because it has a positive leading coefficient. So the max root of U alpha P is at least R, and that's exactly what we want to show, right? Because the new left-hand side, alpha plus das, was exactly R, and we just showed that this is strictly larger than R. So we actually proved the strict inequality which we need if we want to prove the other side of the moreover part, the even only if part. Good. So that was the base case. Let's move to the step of the induction. And again, we want to prove this, and we want to prove it strict when there are at least two distinct roots for P. So to do that, let's kind of define this function phi of P to be exactly what we are trying to prove, but all pushed to the right-hand side. So it's the max root of U alpha P minus alpha, and then I move that to the other side. So really, with that language, what we want to show is that what we want to prove by induction is that for every P in PD, and now this is at least free, phi of P is strictly larger than 0. Right? We want the strict, under the assumption that, so for every P in PD with at least two distinct roots, we want to prove that phi of P is strictly larger than 0. That will complete the proof, because we prove the other part of the moreover. We prove that if you have a single distinct root like x minus lambda 2dd, then equality holds. And now I want to prove that strict inequality holds in the other direction if they are distinct, and if it's the same root, then it's allowed to be with equality. So now that's what we're going to prove. And let's assume a contradiction that it's not the case. So there is px in PD with at least two distinct roots, right? And it's by induction on D. So we're now fixing D equals 3, for example, and so forth. So the assumption is that there exists px in PD for a fixed D. You already handled the previous Ds. So there is a P with at least two distinct roots, which is not strictly larger than 0. It's non-positive. And we can assume again that P is monic because phi doesn't care, right? As long as it's a positive leading coefficient, it may as well be monic. And actually here the proof takes a very nice turn. So we have this polynomial P that we assume by induction causes trouble. Phi of P is smaller or equal than 0. And it's a polynomial. So its root lies in some interval. And so let's denote by minus RR some closed interval containing all roots of P. It doesn't have to be like exact interval containing the roots of P. The minimum and the maximum, just as long as it's a closed interval, it's fine. And let's denote by PD, this kind of PD minus RR, all monic polynomials in PD whose roots are in minus RR as well. Okay, that's kind of maybe the fourth non-trivial thing that we are kind of doing. Like, why should we look at all of these polynomials? So the point is that this set is a compact set, right? It's closed and it's bounded. For us, that would be enough. So it's a compact set. And if you think about it, phi, which takes a polynomial and outputs the max root of u alpha p minus alpha minus, max root of u alpha dp, it's continuous function in the roots of p. Right? Think about it for a second. The roots of a polynomial and the coefficients are of that polynomial are continuous in one another because you can get from one to the other using the symmetric functions and vice versa. So the roots and the coefficients, if you change a little bit the coefficient, you change the root a little bit. I mean, it can change a lot actually, but it's still continuous. It's like it could be exponential change, but it's continuous. And so numerical analysis people will not like this, but it's continuous as a like calculus statement. And this means that if you take p and change a root a little bit, you change the coefficient a little bit, and then here everything is like differentiation is also continuous and so forth. So and u alpha is just subtraction. So what I'm saying is that if you take a polynomial p and change a root a little bit, then phi of b won't change much, right? It's a continuous function in the roots of p, which is a kind of a weird statement. But you have this compact set, and you have a continuous function applied to that and defined on this compact set. So what does it mean? It means that the minimum is attained in the set, right? So there is some polynomial p0 in this set at which phi attains its minimum. So phi of p0 is the minimum. In particular, it's smaller or equal than phi of p, which recall is non-negative, non-positive by the contradicting assumption. Okay, so actually we work with p0, right? So p was a polynomial we assumed exists by contradiction, but to get the contradiction, we'll actually move to p0 and work from there because it's a minimum. It has this property that we can contradict. Now, we may assume that p0 has at least two distinct roots. Why? So first of all, if phi of p0 is strictly smaller than 0, then that's the case, right? Because we proved in the moreover part that a polynomial has exactly one distinct, like one 0, x minus lambda to the d, for that actually is 0. So if phi of p0, I don't know what's the case, but if p of, and none of this happens anyhow, it's all in contradiction. But if phi of p0 is strictly smaller than 0, then that's the case. And if phi of p0 is 0, then you might as well just take p as p0, because it also attains the minimum. And by assumption, p has at least two distinct roots. Okay, so we can assume that p0 in any case has at least two distinct roots. And now let's recall what the pinching lemma tells us. And we're going to apply the pinching lemma and everything from here on p0 rather than on p. So by the pinching lemma, we can write p0 as a p tilde plus p hat. And what do we know about those? So both of them have positive leading coefficients. They are built for induction. The degree of p hat is d minus 1. It's great for induction. And because d is at least 3 in our case, because we did the base case already, d equals 2, we know that p hat has at least two distinct roots. Right? That's good for induction. Because in the induction, that will tell us some things are strict, some inequalities are strict rather than equalities. And we can do induction because of the d minus 1. And we also know that p tilde is also a polynomial whose roots are between minus r and r, right? Because p tilde had this mu as a new root, and mu was between lambda 1 and lambda k, if you remember. So all of its roots are bounded, interlaced between the roots of p0 in this case, sorry. And the maximum roots are all the same for p tilde, and p hat. Okay, so let's say, so by linearity of both u alpha and d, we know that, because of this equality, we know that u alpha d applied to p tilde plus u alpha d applied to p hat is the same as u alpha d applied to p0. And my claim is that the max root of u alpha d p0 is strictly larger than the max root of U alpha dp hat. So let's see why. So that's a claim. So what do we know? So phi of p0 is by definition is this thing. And the pinching lemma tells us that the maximum root of U alpha p0 is the maximum root of U alpha p hat. Alpha is alpha. And if the claim is not true, then there is this non-strict inequality on the other direction, right? So this thing. Okay, so this means that phi of p0 is at least, but could be equal to phi of p hat. But phi of p hat is strictly larger than 0 because p hat has degree d minus 1, and it has at least two distinct roots, if you recall, because d was at least 3 and so forth. And so by induction, we know that this is strictly larger than 0, which stands in contradiction to the fact that phi of p0 is at most 0. Good, so that's the little claim that we proved. And by the little lemma, kind of orthogonal to that, by the little lemma, we also know that the maximum root of U alpha dp0, this is the sum of these two, everything is rooted. So the maximum root of this thing is at most the maximum of the maximum roots of the individual, p tilde and p hat, or U alpha d of those. So what I claim is that actually there is a strict inequality. So the little lemma tells us that there is non-strict inequality, but I'm claiming strict inequality because if you remember, the moreover part in the little lemma says that you have equality only if all three players here are equal. And we just proved here in this claim that they are not, because the 0 player is strictly larger than the hat player. Player is shortened for maximum root of U alpha d of that thing. So there is a strict inequality. And so, okay, so what does that tell us? So let's revisit phi of p0. So phi of p0 is this thing, right? And we know by the pitching lemma that the maximum, the 0 and the tilde parts are equal. And now we just showed this thing, right? This inequality. Oh, sorry. And what I claim is that this inequality holds. So why is this true? I mean, we just showed two. Two means these two stars means that the 0 player is at most strictly smaller than the tilde and the hat. But the claim told us that the hat is smaller than the 0 player. That's how we prove this strict inequality. But let's recall that again, not for the purpose of proving that, but for something else. So the hat is strictly smaller than P0. So this is smaller than that. So the only way that this happens is that this is larger than that. Good. So what I'm claiming here is that the tilde player is strictly larger than the 0 player. So that's why you have the strict inequality here. But really, that's just the definition of phi of p tilde, right? Everything is tilde here. Now, p tilde is also an element here, if you recall from the pinching lemma. That's what I said before. And that's a contradiction to the minimality of p0. Right? P0 was the minimal element there, for which, and now we found some other element there that gets attain a lower value, strictly lower value. Good, so that's the proof of lemma A. It's a bit convoluted, but that's the proof. And before proceeding again in the next video, let me just recap and say where we at. So we want to prove the FFP art theorem. We proved the pinching lemma in the previous video, and now we proved the little lemma and lemma A. Now, for the proof of the main theorem, we're actually going to use this is the green thing here. We are going to use lemma A, of course, but also some of the ideas, this kind of compactness argument and so forth. Also, on top of the fact that it's used inside lemma A. In the next video, we are going to prove two very basic lemmas, which are just called B and C. We are going to state a lemma which is a consequence of something that we are going to do later on, which is I'm calling it lemma D. So just stating it, it's going to follow from something that we are going to do in the next unit, or actually next unit. It's going to be a formula, like an explicit formula for the additive convolution that is going to imply what we are calling at this point in the obfuscated name lemma D. And as I kind of remarked, everything here is assuming implicitly that this is so the additive free convolution is produces a real-rooted polynomial if you start with real-rooted polynomials. So that's something kind of we assume at the ground level, and we are going to prove that as well. But that's later on, and that's something that we already swallowed at this point. Good. So again, next up, we are going to do lemma B and B and C, state D, and prove this theorem. Okay, and then these are different units that we are going to do afterwards. Okay, quite technical, but it is what it is.